Hello everyone, welcome to my video on the proof of the limit as theta tends to 0 of sine theta over theta equals 1. So we're going to prove this statement here. We used this statement in a previous video where we showed that the derivative of sine is cos and the derivative of cos is negative sine. So let's complete the proof by showing that this statement that we used is in fact true. So let's go ahead and look at the proof. So let's focus on a unit circle just to get an idea. But I'm just going to focus on the first quadrant of the unit circle. So I'm going to just expand, give myself some room. This is the y-axis, this is the x-axis. And then we have, pretend a giant circle, but I'm just going to draw the top right of the circle. Okay. So this is a unit circle, meaning that from the origin to the circle, it's a radius of 1. So this is a distance of 1. It's called the unit circle. And what we're going to do is essentially take a line segment and we'll call the angle here theta. Okay. So we'll call the origin O. This line segment that we drew, let's call this point here B. And then we'll draw a line going straight down at point B. We'll call this point here going straight down A, and we'll call this point over here at the edge of the circle C. Okay. So the observation that we have to make in this case here is that notice that the line segment A to B is definitely smaller than the next line segment that I'm going to draw. Let's do this in green. The line segment from B to C that I'm drawing in green. Okay. And that line segment that I just drew in green is definitely smaller than the arc length from B to C. This is the observation that we're making. So let me draw the arc length in red. And let's explain this a bit more. So the observation that we're making is that the line segment AB, so AB, line segment AB, is smaller or equal to our line segment BC, which in turn is smaller or equal to our arc length BC. Okay. So this is the observation that we start off with. Okay, so note that this here is in fact true. Why is it true? Well, let's think about it a bit. AB is this line segment that I drew that was straight down, right? So the angle that we have here is a 90-degree angle, right? So if we focus on the small little triangle that I drew here, ABC, notice that we have a right angle triangle, right? And if AB is the height, and this is the 90-degree triangle, we know that the line segment BC, this one that I drew in the green, the dotted green line, is the hypotenuse, because that's a line segment that's across the 90 degree. So it's opposite to the 90 degrees, so this has to be the longest side by definition, just by Pythagorean theorem. Okay, so BC is definitely bigger than AB due to Pythagorean theorem. So this statement holds. Now, why is the red line, the red arc line, larger than the green dotted line that I drew? Well, the shortest distance between any 2 points is a straight line. So B to C is just a straight line. So the fact that you're taking an arc, you're going a longer path, right? So BC, the arc length BC has to be larger than the straight green line that I drew, okay? So this is the observation that's made. This holds true. Now let's go ahead and find these distances. So what we're going to use is our trig ratios from high school, and we're going to use the fact that from this angle that we drew here, we want to represent AB in terms of theta. To do that, we could express the line segment here, BC, as, I just want to mention one more thing. The line segment OB here, since this is the distance from the origin to the circle, this is a radius of 1. It's a unit circle, so the radius is 1. So the distance between O to B is 1. And the other distance from O to C is also 1, because that's the radius as well. Notice that C is a point on the unit circle. Therefore, the distance from from the origin O to C is also 1. Okay, so keep that in mind. So what we want to do is find the distance AB. Using our trig ratios, we're going to use opposite over hypotenuse. Okay. So we know that sine theta is equal to opposite over hypotenuse. This is our trig ratios that we know. Okay, so sine theta in this case, if we focus on the triangle OBA, then the opposite to the angle would be the line segment AB. And the hypotenuse, if this is our 90 degree, the hypotenuse would be the longest side OB, which is 1. Okay. So this tells us that AB, if OB is 1, the line segment AB is being divided by 1 is equal to sine theta. So at the end of the day, the line segment AB is just sine theta. This is what we showed here using our trig ratios. Okay, so this line segment here, the one that's straight up, this is really just your sine theta. Okay, and we already know this really because we know from our unit circle that whenever you have a point on the unit circle, let's look at B, we know that the unit circle X and Y, the X value is really our cos theta and the Y values are really our sine theta. And this is what we're showing here, that the height to get to B, which is our Y value, of this point here is just sine theta. So we know every point on the unit circle can be expressed as cos theta, comma, sine theta. And that's the value B. If you wanted to show this as well, you know the distance from O to A is really just cos theta. Why? Because cos theta from this angle here is adjacent over hypotenuse. Since the hypotenuse is 1, this distance from O to A is just cos theta. Okay, so we're using this information. So we know that AB can be rewritten as just sine theta. So from our observation up here, AB is just sine theta. So let's write that down. So instead of writing AB, we're going to write it in terms of theta, which we just showed in black. So this is sine theta. And that's smaller or equal to BC. Let's go ahead and figure out what BC is. Let's do this in green. So for BC, this one for now, let's just leave it. We don't know much about BC. Leave that in green. And let's move on to the arc length BC. What do we know about the arc length BC? Well, the arc length BC by definition is just the angle in radians, right? We know that S equals r theta. The arc length, which we use the letter capital S, is equal to the radius times theta. But in this case, since we have a unit circle, the radius is just 1. So we know that the arc length, S is arc length, this distance here, is equal to 1 times theta. So the arc length is directly equivalent to the angle in radians. So instead of writing BC, we're just going to use the angle which we're using, which we call theta. So this is less than or equal to theta. Okay. So from our observation, we have this inequality over here, and what we're going to do now is just divide the entire inequality by theta. So we're dividing by theta, which is a positive angle, so we don't flip the inequality sign. So divide all 3 sides by theta, and this gives us our first inequality. That's sine theta over theta is smaller or equal to BC over theta, which we kind of ignore for now, and we say that this piece here is smaller or equal to what we have in red here, theta over theta, which is 1. And this gives us our first part of the proof. So now for the second part of this proof, what we're going to do is we're going to extend the line of OB. So what we're going to do is extend it until we have a 90-degree angle with OC. So let's move this. Extending this line until we have a 90-degree angle with OC, we have this new triangle here. We'll call this point D. So we extended this line straight out, and now we have this new big triangle OCD. This is a 90-degree angle. It's hitting the point C at a tangent. Okay, so it's hitting it at a 90-degree angle. And the observation that we have to make here, actually before we do an observation, let's take out this green line here, because now we're focusing on this big triangle, and what we're going to do is take the tangent at point B as well. So we'll use this in green, and we'll use a tangent line here. Let's say I have a tangent line. This again is hitting at 90 degree. and we'll call this new point here E. Okay, so we took the tangent at point B, and it hits the line segment CD at point E. Okay, why are we doing this? Well, now with this extension that we created, the observation to be made is the fact that the arc length BC, so BC, arc length BC is smaller than BE plus EC. This is smaller or equal to segment BC plus, sorry, BE plus EC. Okay, let me maybe do this in green. Just to make it a bit more clear. BE plus EC. Okay, that's the observation we're making. So I think this is obvious. We have our arc length here, BC. If we take the tangent BE, that's definitely smaller than BE to EC, as on the green line we extended outwards. So that's definitely larger than this. And then the next statement that we're using, I'll do this in black, is that this statement here is smaller or equal to BE, sorry, the claim that we're making here is that BE is smaller than ED. Why is that true? Why is this distance here smaller than this distance here? Why could I make that that claim? Well, the reason why I'm allowed to make this claim is because if you look at the triangle BED, by definition, this line segment that we drew here is a tangent, which means it's a 90-degree angle here. So we have a 90-degree triangle. And again, across the 90-degree triangle, this side here is the hypotenuse. So since this is the hypotenuse, ED is the longest side of this triangle. So it has to be longer than EB and BD. So the claim that we're making here is that DE, this distance here, is bigger than BE. And EC and EC are the same. So this statement is true compared to this. Okay, so now we're at this part here. So what we have is the arc length BC is less than or equal to DE plus EC. DE plus EC is just the line segment. This piece plus this piece is just CD. So this is equal to CD, line segment CD. So the observation that we made is that the arc length BC is smaller than this line segment CD. Okay, and from that, what do we get? Well, what is the line segment CD? Essentially, what we're trying to look for is the point D. What is this point? Well, the x value of this point, we know it's on the unit circle. Therefore, the radius here is 1. So the x value to get to point C is 1. And since C is what's it called, a tangent, then this point D is right on top of C, meaning the x value here is also 1. Next, what we have to find is the height. How do we find the height? Well, the whole thing is a 90-degree triangle. Again, this is a tangent to point C, so this is really just a 90-degree angle. Since this whole triangle is a 90-degree angle, we can use our trig formulas again. So we're going to use opposite over adjacent. So we know that tan theta is equal to opposite over adjacent. And tan theta is equal to opposite, which is the line segment CD, over the adjacent, which is the line segment OC. But we just said that OC is the radius of the unit circle, which means that this distance here is just 1. So what we get is that line segment CD is just tan theta. So CD is just tan theta. Okay. So we said before that the arc length is essentially just the radius, because the arc length is equal to the radius times the angle. The arc length is just the angle theta. That's what I meant to say, not the radius. So the arc length we saw before is just theta, right? Because S equals r theta. The arc length is equal to the radius times theta, and the radius in this case is 1. So the arc length is just equal to theta. So BC here is just theta, and that's smaller or equal to all this stuff, which eventually is the upper bound here is tan theta. So we get this statement. This observation leads to this statement here. Theta is less than or equal to tan theta. Let's keep going. So what does that mean? If we solve this, we know that tan theta is really just sine theta over cos theta from our properties. Okay. And now we could kind of cross multiply cos theta up here and divide by theta. Multiplying both sides by cos theta gives us the cos theta here cancel, we're left with sine theta. And here we're left with cos theta times theta is smaller or equal to sine theta. So this cos theta is cancelled, leaving us with sine theta on this side, that's bigger or equal to. And here we have cos theta times theta, right? And now we divide both sides by theta, giving us cos theta is smaller or equal to sine theta over theta. This is the second inequality that we need. Okay, the first one was up here. We showed that sine theta over theta is less than or equal to 1. And here we have cos theta is less than or equal to sine theta over theta. So let's put this information together. So the first part of the proof, we showed that sine theta over theta is less than or equal to 1. That's what we have here. And the second part of the proof, we showed that cos theta is less than or equal to sine theta over theta. Okay, so we got this sine theta over theta, and it's bounded below by cos theta and bounded above by 1. All we're missing now, so we have this piece, all we're missing is the limit. So what we're going to do is take the limit on both sides of the equation. So if we take the limit as theta goes to 0 of cos theta, that's going to be smaller or equal to the limit as theta goes to 0 of sine theta over theta, which is smaller or equal to the limit as theta goes to 0 of 1. Okay. So taking the limit on all sides, what we get is on the left hand side, limit as theta equals to 0 of cos theta. We direct substitute theta with 0, so we get cos of 0. Here we have limit as sine theta, limit as theta goes to 0 of sine theta over theta. And here we direct substitute, theta is going to 0, but there's no 0. So this is, there's no theta here, it's just 1, so it's just equal to 1. And we know that cos of 0 is equal to 1. So what we have here is that the limit as theta goes to 0 of sine theta over theta is bigger or equal to 1, but at the same time smaller or equal to 1. How's that possible? How could this thing here be smaller or equal to 1 and bigger or equal to 1 at the same time? The only way for that to be possible is that if this thing here is equal to 1. We're using a squeeze theorem argument. So it's squished between these two values, therefore it has to go to this value here. So by squeeze theorem, we have obtained that the limit as theta goes to 0 of sine theta over theta is equal to 1. And this is the end of the proof. So the next claim that we have to prove is the fact that the limit as theta goes to 0 of cos theta minus 1 over theta is equal to 0. So this is another limit that we used to prove that the derivative of sine is cos and derivative of cos is negative sine. So we have to prove this statement as well. It's a lot easier than proving the statement that sine theta over theta is equal to 1. But since we proved this already, now we can use this. And let's go ahead and show that this statement is in fact true. So we have the limit as theta tends to 0 of cos theta minus 1 over theta. And in order to get the proof, the trick is to multiply by the conjugate. So we're going to multiply the top and the bottom by cos theta plus 1 and cos theta plus 1. Okay. So it's a fancy way of just multiplying this by 1, giving us limit as theta goes to 0. Cos theta times cos theta is cos squared theta. Cos theta plus 1 times plus 1 is cos theta. Negative 1 times cos theta is minus cos theta. These guys cancel. And then minus 1 times plus 1 is just minus 1. And on the bottom we have theta times cos theta plus 1. Okay. So on the top, what we're left with is cos squared theta minus 1. The property we have to remember is the fact that sine squared theta plus cos squared theta is equal to 1. But we want cos squared minus 1. So what we could do is take this 1 on the right side and bring it to the left side. So we get cos squared theta minus 1 equals, and the sine squared theta at the same time, I'm going to bring it on the right side of the equation, so it becomes minus sine squared theta. So this says that cos squared theta minus 1 is equal to negative sine squared theta. So cos squared theta minus 1, we're going to rewrite it with this, giving us limit as theta tends to 0 of negative sine squared theta on top over theta times cos theta plus 1. Okay. So this was this property here. And now we just split it up cleverly. The way we're going to split this up is limit as theta goes to 0. I'm going to take one of the signs on the top into theta. So I'm going to have sine theta over theta multiplied by, we have a negative sine theta left over cos theta plus 1. Okay, so we have this piece and we have this piece. And we're taking the limit of both these pieces as theta tends to 0. Well, look at this piece, the first piece. We have sine theta over theta. We know this already. We proved that sine theta over theta is equal to 1 when you're taking the limit as theta goes to 0. So this piece here is just 1. So this is gone. So all we have to focus on is this piece here. And here we could just directly substitute theta with 0, giving us negative sine of 0. And then I'm going to replace theta on the bottom with 0 over cos of 0 plus 1. Sine of 0 is just 0. So we get negative 0 on top. And on the bottom, you have cos of 0, which is 1 plus 1. This gives us negative 0 over 2, which is just 0. And we proved the claim. We proved that this limit here is in fact equal to 0. Okay, so let's take a look at a couple of examples and apply these limits. So in our first example here, it says to evaluate the following limit. The limit that's given is limit as x tends to 0 of sine of 5x divided by x. So let's go ahead and do this. A note I just want to point out is whenever you're using our property, the limit as theta goes to 0 of sine theta over theta, it's equivalent to actually taking the reciprocal. So since this is equal to 1, it's equivalent to saying that the limit as theta tends to 0 of theta over sine theta is also equal to 1. Okay, so that's an equivalent statement. And same for cos. The one that we proved for cos was the limit as theta goes to 0 of cos theta minus 1, all that over theta. Well, it's equivalent to saying, instead of cos theta minus 1, we could take the reverse order and write it as 1 minus cos theta over theta, and taking the limit as theta tends to 0, and that's equal to 0. Okay, so these two are equivalent statements, and this is an equivalent statement as well. Okay, so you might have to use these limit theorems or limit statements in different forms. Okay, so the first thing that we have here is limit as x tends to 0 of sine of 5x over x, and the idea is you want sine theta divided by theta, right? So what this is saying is whatever's in the argument of the sine, whatever the angle is, we want the same thing on the bottom. So here in the argument of the sine, in brackets we have 5x. So on the bottom, what do we want? We want 5x as well. How do we get a 5x over here? Well, the x is already there. What we could do is multiply the top and the bottom by 5. Okay, so we multiply the top and the bottom by 5. And now whatever's in the angle is equal to the denominator. So since we're taking the limit as x goes to 0, this whole piece here, sine of 5x over 5x is equal to 1 using this argument up here. Okay, so we're just left with the 5 on the outside of limit as x goes to 0 of sine 5x over 5x. This piece here is equal to 1, meaning the answer is 5 times 1, which is 5. And we're done. Okay, so let's look at another example. So in the next example, we have to evaluate the following limit. Limit as x goes to pi of sine of 7x divided by 7x. So pause the video, try this on your own, see if you can get it. Okay, so if you tried the question and you got the answer is 1, that's wrong. Be very careful. You cannot apply the limit statement that we have up here. Okay, this theorem does not apply because this only works when theta or your x goes to 0. In this case here, it's going to pi, not the same. Okay, so you have to be very vigilant. You have to, in order to apply this, the limit has to be sine theta over theta as theta tends to 0. Since we're tending to pi, we direct substitute and you get sine of 7 pi over 7 pi. Okay, sine of 7 pi is just 0 divided by 7 pi, and this gives us 0. So the answer to this limit is 0. Okay, now 1. Be very careful, make sure when you're using these terms it's of the correct form. So here in example 3 we have to evaluate the following limit. The limit that's given is limit as x goes to 0 of tan of 3x over 4x. So pause the video, try to see if you can get this on your own. Again, this is kind of a trick, but can we apply this theorem? Well, the answer is right now no. As it stands, no, because we don't have sine, we have tan. How do we deal with this? Well, the game plan here is to rewrite tan in terms of sine. We know that tan is equal to sine over cos, so let's go ahead and do that. And if you tried right away direct substituting the x into here, that's a really good attempt. But in this case here, if you direct substitute, you replace your x with zeros, you get tan of 0, which is 0, and you're dividing by 4 times 0, which is again 0. So you have 0 divided by 0, we get an indeterminate form, we're still stuck. Okay, so the game plan here, the trick is to rewrite tan in terms of sine and cos. So this here is equal to limit as x tends to 0, and we're going to rewrite it as sine of 3x over cos of 3x, and we have the 4x on the bottom. So this piece here is just the tan, and we have the 4x on the denominator as well. Okay. Writing it like this is a lot better. So now what we could do is separate this. We could write this as sine of 3x divided by, I'm going to take the x, and now we're left with times 1 over 4 cos of 3x. Okay, so I'm just ignoring this piece for now, and I took the x and put it underneath the sine of 3x. Why am I doing this? Well, I'm trying to get this form. I'm trying to get sine theta divided by theta, or sine of its angle divided by whatever's in the angle. So here we have the 3x in the angle. I want 3x on the bottom. We have the x, let's put in the 3. How do we do that? Multiply the top and the bottom by 3. Okay. And now that we're taking the limit as x goes to 0, this piece over here, we know, is equal to 1. So all we're left with is the limit as x goes to 0 of, okay, this here is equal to 1. We're left with 3 on the numerator, and then 4 cos of 3x on the denominator. But the issue is here, we can't use our theorem with cos in it because we don't have cos theta minus 1 over theta. The cos is on the denominator. How do we do this? Well, at this stage here, we could direct substitute because we won't get 0 over 0. It's not an indeterminate form anymore. So direct substituting at this case solves the problem. So we have 3 on the bottom, 4 times cos. We're replacing the x with 0, so 3 times 0 is 0, and we know that cos of 0 is just 1. So this thing here is just 3/4. And that's the answer. So this next example here, example 4, again, evaluate the limit. The limit as x tends to 0 of 5x times cot of 2x. So this one here, again, pause the video, try it on your own. Very difficult because it doesn't even have a fraction. In order to apply this, we need a fraction. So how do we do that? Let's go create a fraction. How can we do this? There's different ways. The way I'm seeing it right now, you could rewrite cotangent as 1 over tangent, but the way I'm thinking of it at this moment is to rewrite cotangent as cos over sine. Okay. So this is the property that I'm using. If you wrote 5x over tan x, 5x divided by tan of 2x, that should still work. You could still get the answer, but the way I'm seeing it, I'm going about it this way. And now we have sine of 2x on the bottom, and we have 5x on top. So again, I'm going to rewrite this, move things around. I'm going to write the x over here over sine of 2x times 5 and cos of 2x on the top. Okay. So here again, my argument of the sine is 2x. So I want a 2 on the top. How do we remedy this? Multiply the top and the bottom by 2. Okay, this is good. Notice the 2 on the denominator is, like, you shouldn't be thinking of it as 2. You should be thinking of this as 1/2, right? Because the 2 is on the bottom, it's on the denominator. Okay, so this over here, 2x over sine of 2x as a limit as x goes to 0, this whole thing is equal to 1. We're using the property, the inverse property. Okay, so 2x is just on the numerator, sine 2x on the bottom. This is still equal to 1, that's fine. And we're left with the limit as x tends to 0. On the numerator, we have the 5 cos of 2x. And on the denominator, we have this 2 that we didn't use. Okay, and now we direct substitute again. So replacing your x's with 0, we get 5 times cos of 0 over 2, which is 5 halves. And we're done. Okay, let's look at our final example. So in this example here, we evaluate the following limit. The limit that's given is 1 minus cos of 3x divided by sine of 2x as x tends to 0. So let's go ahead and solve this. Again, pause the video, try this on your own, see if your answer matches mine. So the first thing I'm going to do is separate this. I'm going to write it as 1 minus cos of 3x over, let's say, 1 times 1 over sine of 2x. Okay, and now we see the game plan. So the game plan, 1 minus cos of 3x is what we have up here, 1 minus cos of theta. We want to divide by the angle of the cos, so we want a 3x on the bottom. So what am I going to do? I'm going to multiply the bottom by 3x, and I'm going to multiply the whole top by 3x. Okay, and same thing here. I have sine of 2x in the bracket. I want a 2x in the numerator, so I'm going to multiply the top by 2x and multiply the bottom by 2x. Okay. So since we're taking the limit of this thing and this thing, we know that this piece here, 2x divided by sine of 2x is equal to 1 as the limit as x tends to 0. This is equal to 1. And we know that 1 minus cos of 3x divided by 3x, this piece here, goes to 0 using this theorem over here. And here the x's cancel. So what we're left with is 3 on the top times 0 times this is 1 and times a half over here. Since we're multiplying by 0, this whole thing is just equal to 0 and we're done. Okay. So I hope this helped. I hope this was useful. Keep practicing and I'll see you in the next video.